Hi, everyone. Welcome to the 112th MedAI group exchange sessions. And this week we have Wang here with us to talk about his work on radiologist-centered AI with eye tracking. Bin is a second-year PhD student in the Department of Electrical and Computer Engineering at Northwestern University, and he's advised by Professor Ullas Bakci. He's mainly working on developing human-centered AI for medical image analysis, and his interests include eye tracking, multimodal foundation models, and human-computer interaction. So, Bin, I guess before we get started, do you have any preferences on how you'd like to take questions?
I can do whatever you want, yes.
Okay, so I guess it's okay to interrupt you during your presentation.
Yeah, it's fine.
Okay, perfect. So let's try to make this session as interactive as possible. And without further ado, let me hand it over to Ben.
Okay. Thank you guys for inviting me here to give this talk. My name is Ben. I'm right now a second-year PhD student at Northwestern University, and my advisor is Professor Ullas Bargi. Today, I'm going to talk about the topic named Radiologist-centered AI with eye tracking techniques. So first of all, let me ask one question. Do you guys think can or will AI replace the radiologist or physician in general? So this question is being asked pretty often during my conversation with the radiologist. So sometimes they're quite worried about in the future they might be replaced. Yeah, and there's already many news discussed about this. Like this one, the title is "Could AI be your next radiologist?" And also some studies in like Johns Hopkins, they are study like explore the potential of AI in the reading room, and even the Professor Andrew. One time he said, should a radiologist be worried about their jobs? Breaking news, we can now diagnose pneumonia from chest x-rays even better than radiologists. So this news actually is pretty scary, but from my point of view, I still think it's a long way to go for the AI to be involved in the radiologists because there are multiple challenges. The first one is I think it is pretty hard for the deep learning model to localize the lesions, especially in some challenging cases. So I put one case here. Um, these two images is one patient, and this patient has bilateral multifocal areas of consolidation. And red bounding box means it is the real lesion area. And we wish the model can find out, like, pay attention on these areas. But this study, they try many different deep learning models like these two. The first one, it's just focus on one of the lesion part and miss the other one. And the second models, it's just simply focus everywhere of the lung part. So it means that for this kind of challenging cases, normally it is hard for the models to localize on the lesions if there's no fine grain expert knowledge. So the second challenge is that right now the current deep learning model is lack of expert knowledge. So it is especially pretty obvious in the disease classification task. I just put a very, very simple framework. Like it's also most commonly used in the field. They just input the radiology input images into the neural network and let the network to learn the classification labels given so that the network can predict the probabilities of the disease of this patient. Notice that this kind of frameworks only use the classification labels which is given to learn how the disease look like. So the network only had a kind of like a number to learn. It doesn't have like fine-grained like segmentation mask or bounding box, those things. It is pretty hard for this kind of network to learn how the disease look like and which kind of a region is important. So our motivation is just to build radiologist-centered AI. We want to fully utilize the expert knowledge, learn how radiologists read, so that we can design a kind of computer-aided system that is used to assist the radiologist instead of replace them. So it will somehow in the future reduce workload of the radiologist instead of just kicking them out, right? So in our study, we find out that eye tracking is actually one way to include the expert in the loop. We're trying to use the eye tracker to record radiologist eye movement. So you see from these images, there's a person looking at the monitor screen, and also there's a blue square under the screen represent the eye tracker. So this small eye tracker will record which places the human is looking at on the screen. So on the leftist image, this is actually the setting in our lab. We built this kind of system to collect the data. So this is our own designed software that is used for the radiologist to read images and also to measure everything is there. And also there's a small eye tracker that is used to track the radiologist eye movement. After the post-process, we will get this kind of data, like we will know, like highlight region that the radiologist spend a lot of time there. So now with this kind of eye tracking technique, how to apply them in the real medical image analysis application, I will discuss two today. The first one is called GAZE-GNN, a gaze-guided graph neural network for chest X-ray classification. So it is already published on WACV 2024. And we know that for the chest X-ray classification, there's some challenges like this one. Chest X-ray has limited soft tissue contrast because it is a 2D image, right? And many tissues such as organs, blood vessels, and muscles, they have similar intensity values. So you see from this case, the heart and the pneumonia, they overlap together. So it is hard for the deep learning model to localize the real abnormality. So our motivation is that we used eye tracking technology to collect the eye gaze from radiologists. And this kind of eye gaze, it contains the location information that radiologists have fixation during the diagnostic. And it will have the potential of nullity or important regions, which is especially the challenging cases will not provide. In this way, we will supplement more human attention into the deep learning model. So the model will not just learn like only learn based on the classification label, right? Now we have more expert knowledge. So it is more kind of like an interpretable way. And to apply the eye tracking into the disease classification, there's already some solutions. In my work, I just group these all previous studies into two groups. One of it called attention consistency architecture. So you see, this is the framework. It accepted the image as the input and input it into an encoder, get the image features. After that, it input the features to a decoder and get a class activation map, just like a machine attention. So from another side, they just used eye gaze to generate a vision attention map. So it is kind of like a human attention. They try to minimize the difference between these two kind of attention map and let the model to learn how human read images. Sorry. So this kind of frameworks, it consider eye gaze as a supervision source. So it will bring some trouble, like during the inference part, there's no eye gaze data. And we did some experiment showing that if we test this kind of model on the dataset with distribution shift, with the training part, it will have very huge performance drop because the model already learned based on eye gaze, right? Now in the inference part, you don't have eye gaze. How can I know, right? So this framework is a little bit not so robust. And the second,
Ben, I think we have a question from the audience. Is eye gaze a CNN-based tool?
sorry, is eye gaze in CN what?
is eye gaze a CNN-based tool? That's a question from the audience.
What do you mean by student?
I think Ben, what they want to mention is that your encoder is backbone is CNN or not?
Oh. So yeah, this I will discuss this more detailedly actually. So this encoder can be used transformer, CNN, graph neural network. Like this is just encoder, right? So this framework is pretty flexible. And now I'm just talking about the framework right now. And in the later slides, I will discuss more about nowadays how the current studies apply and what they use.
So, thanks, Ben. So I have one quick question. So since you mentioned that you are collecting the eye gaze data and calculating the VM and then passing to the encoder, how you are doing it? Like how many seconds you need the VM to collect for the eye gaze? Do you have a time requirement for the radiologist, or it's also flexible?
You mean during the data collection stage?
Yes, during the data collection stage.
So actually we do not have time requirement. We just because this study have like two stage. The first stage is that we collect the eye gaze from radiologist
Right.
and then we analyze it.
So did you have any kind of like session? How long does each session for the radiologist would be for every image, or it's also flexible that you didn't have any requirement?
So actually, we want to, in the future, build a kind of system that in the real reading room, the radiologist can use the eye tracking technologies. So this study is just to enable this kind of technology to be used in the reading room because we process the eye gaze data pretty fast. And the current previous studies, they process the gaze data pretty slow. And in this study, we just find out how to make it quicker.
Okay, so you did it on the 2D images then. You did it try the 3D volumes?
Yes, actually, this study is based on the X-ray image, but we have other study based on the 3D cases, but
Okay.
it's still ongoing.
Okay.
Okay, I'll continue. So, yeah, I finished the first current solution, and the second one is called two-stream architecture. And so it is have two branch. One branch is used to process the image, get the image feature, and another branch is to get the get the gaze feature. So it first generate the vision intention map based on the eye gaze, and then do the concatenate between the image feature and the gaze feature, and send them into the classifier, get the prediction. So here, this framework has an issue that it transferred the eye gaze into the visual attention map for each case during the inference. So the generation of the visual attention map is quite time consuming. We did a test there's two reasons why it is very slow. One reason is that you see there's multiple gaze points that like red points is everywhere, and you can see it's pretty huge amounts of the points. And if you want to get this kind of heat map, it will cost you some time. And another reason is that the X-ray image is like high resolution. So the image size is, if you want to have a perfect attention map, you just need to do based on the high resolution. So it will bring some time consuming part here. So we know that if the generation of the visual attention map is pretty slow, how can this kind of study be used in the real world clinical diagnosis? It is not realistic because the radiologist will not wait like 10 seconds for each patient and to use the AI suggestion, right? So in my method, we still embed the eye gaze in inference, like just like two branch, two stream architecture. We have two branch. We incorporate eye gaze even in the inference part. And another side is that we get rid of the visual attention map generation. So it is called gaze embedding, and I want to discuss about it. So this part will make the whole processing of the eye gaze more fluently and more quick. So our method has two strands, like robust and time efficient. So this
quick question here, Ben. So
Yes.
just to make sure I understand correctly. So the expected workflow is you'll have the radiologist and your gaze GNN together to make it better for the radiologist, or is it going to be without any expert in the loop? You will want to deploy this.
So actually in the study, we wish to have the radiologist in the loop, right? So once there's an image feature, and this is image in this branch, and another part we want to, like in the reading room, we ask the radiologist first to read this image, and after the reading of this image, we collect the data, and the whole processing of this branch will be pretty fast. So radiologists just sit there and we wait the processing of this whole pipeline and get the AI suggestion. So that's what we want to see.
Got it. Okay.
So this slide showed the overview of our framework. So two branch. The first branch is that I crop the image into multiple patches. And after the patches, we extract the feature based on the image, so we can get the patch embedding. So in another branch, we have eye gaze here. So you see there's a red point, right? The bigger the red point is, it means that the radiologist spend more time there. And so we apply a little technique here called time aggregation. It is pretty simple. So it is used to replace the visual attention map generation. It means that we just do a kind of summation in the, in this patch. So it means that if the patch is more red, it means the radiologist spend more time on this region. So after that, because the patch is like coupled together, we can easily do the fusion of different type of data, right? So we do the position and gaze and also the patch embedding here. And after that, we just kind of build many graph node. And based on the node, we build a graph construction here. And after we get the graph, we send it into a graph neural network and get the predicted probabilities. And here, each node will represent two kind of information. One information is the image side, and another information is the gaze side. It represents how important this node is. So
sorry, Bin, one quick question. So one thing is like you are predicting chronic heart failure. CHF, what does the CHF column means?
Yeah, this is one of our final label.
Wow, because you understand, like chronic heart failure is not the diagnosis that people usually do from chest X-ray.
Oh, because like you said, it might be not so common. We just trying to use a public data set which has the eye gaze data and also the diagnostic from the radiologist. So in that public data set, they have three labels: just normal, heart failure, and the pneumonia.
Okay. That is kind of strange. I don't know like where the radiologist should look when it's a chronic heart failure, because they can look at the heart, but you cannot really probably see anything in the heart for heart failure.
Yeah, I agree with you. It might be the shortage of the 2D image eye tracking application. So we might need more like 3D application. Okay, so for the time aggregation, I already discussed, it is pretty simple. We just need to sum up all the eye gaze points fixation time inside one patch to represent the attention feature of the patch. For the graph neural network, it is the like.
Ben, I think we have a question from Ramon.
Yeah.
Ramon, you just want to ask, or I can read it for you.
Yeah. So are patches extracted based on landmarks? I'm just curious how orientation differences in the patient may influence the model.
Oh, you mean the orientation of the patient?
Yeah, because sometimes they might be oriented slightly different. So not every patch would match 100% for every patient. So.
Oh, so actually you see here, the patch is pretty big, right? But it is not like this during the training or the testing. The patch is just showing you there's a patch here. In the real cases, the patch is kind of not so big. So I think that will not bring some noise, as you said.
I see. Thank you.
And for the graph neural network, it consists of L graph processing blocks and also a average pooling layer, a graph classification head, just like this. For the graph processing block here, it is consist of multiple fully connected layers and a graph convolution layer.
I have a quick question here. So your graph structure, is it based on like just spatial connections between different patches?
No. Actually, we will calculate, because let me see here. So here in this stage, I will get a bunch of features, right?
Mhm.
We take each feature as a graph node and calculate the k nearest neighbor of each node. So
Oh, okay.
we find the nearest neighbor and build this graph. So you
And
see the
did you?
green one. The
Mhm.
green one will represent a kind of semantic in the image, and
Oh, okay.
blue and the yellow, they all represent different kind of semantic in the image.
And in your experience, like, did you have to put did you have to play with the threshold? Because in some cases, like your graph may become like too dense, or does it not happen in this kind of data?
Yes, we test that and choose the one that is best.
Okay. And then you're also talking about this L layers of graph processing. With graph neural networks, there is the trend of homogenization. If you have like too many graph processing layers, so just out of curiosity, like what L is like an optimal. How many layers did you actually use for this model?
Okay. For this one, we actually have I think there's around 10 for the detail. I
10.
don't remember. So it's not too deep and not too shallow. So
Mhm.
it's just there. We try a bit and to find
Okay.
out how it can work.
Okay.
If you want to know detail, you can check this paper. It is all.
Okay. Thank you, Omicron.
So why in the study we apply the graph neural network based on instead of the transformer, instead of the CNN? There's also the question here before. So we find out that the graph neural network is not so data hungry as the transformer-based models. And you can see here we test on the swing transformer, and we also test on the vision transformer, but for the space limitation, we did not put there. But it's similar performance as the string transformer. But we find that the graph neural network achieved better because in the eye gaze application, the data is very, very limited. And for that public data set, I think there's only like 1,000 cases, more than 1,000. So if one to use the transformer, it is a hard thing because the transformer is data hungry. And another reason is that for the graph neural network, it's more flexible to represent different types of information in single graph node, because I explained here, for a single node, it will contain multiple information, like not only the image, but also the gaze pattern. So that is also the strength of the graph here. After that, we do a classification accuracy experiment. We find that our model achieved the best accuracy nearly on all the evaluation metrics. You see the accuracy, we improve like multiple points. For the AUC metric, we also compare with the state of the art, and we find that we outperforms the model with the best average AUC. Now we're gonna talk about how the inference speed is improved. So because we want to bring this kind of technology into the reading room sometime, so it must require huge, faster processing speed of the pipeline. So here we find that the two-stream architecture I just talked about, it spans the 9 seconds for each patient because it encompasses the gaze in the loop. And for the attention consisting architecture, it spans less, like 0.2 seconds, but it does not require gaze in the inference stage. But for our method, we have the gaze embedding in the inference part, but we just reduce the inference time significantly and make it comparable to the one that does not use the gaze. And for the comparison of the robustness, we did an experiment that we tested our model and also the state-of-the-art model on the dataset that has some distribution shift to show that our model is more robust, because we find that the attention consisting architecture, if it is tested on the the dataset that has distribution shift, it will have huge performance drop, but our model have like not too much. Now let's have a look on the visualization. So you see this column is the original image, and this column is the eye gaze, represent the radiologist attention. And this column means the model attention that does not have eye gaze integration. This column has the model attention that has the eye gaze integration. So we can see that somehow the eye gaze will help the model to correct the region that should be focused on. Here. Yes. So let's have a summarize on this study. So in this study, we bypassed the time-consuming visual attention map generation, significantly increased the inference speed. Also, we encompassed the eye gaze during the inference, which shows the strong robustness in the experiment. We achieved the state-of-the-art classification accuracy and a strong robustness with time-efficient performance. More importantly, this study will kind of prove the feasibility of bringing real-time eye tracking techniques to the radiologist's daily work. Now, we have already talked about how we can apply the eye tracking technology in the classification task. Now, we trying to apply them on other tasks like the organ segmentation. In this study, it is named the GazeSam Interactive Image Segmentation with Eye Gaze and Segment Anything model. It is already published on Europe's workshop last year. So this study mainly investigates how to make the data annotation procedure more fluently. So we know that the data annotation is quite time-consuming and labor-intensive, especially for the image segmentation task, because it also in the high-risk tasks like the radiologist, it requires more efforts, and also we can only ask the expert to do it. So it is kind of like more expensive. Current solution is that they have several interaction types like clicks, scribbles, bounding box, and polygons. They just click on the object, and then the algorithm will show you a segmentation mask. But the drawback is that all of these interaction are based on mouse interaction. So there are two drawbacks, like annotator will easily get tired after repeated clicking, right? Because it is boring. And once the annotator feels tired, it will largely decrease the efficiency of the data labeling. So this is the drawback of the mouse interaction, because they need to repeatedly click the mouse. So why are we trying to bring the gaze interaction here? You see here in this lady image, there's a lady, we want to segment her body. If you want to do the mouse-based interaction, you need to click multiple times from head to other part. So it's like once you click, you need to move to another place. And we did a test that it might cost around 1.5 seconds. But for the eye gaze-based interaction, it is different, because you just need to have a glance on this lady, right? You can just first look at the head, and then the body in the middle, and then body in the bottom. So it is pretty fast. Just have a glance, and then the segmentation is showing. So we test it is like less than 1 second if you do the interaction like this. So the motivation how we use the eye gaze as a new interaction instead of mouse is that it is more natural, intuitive, and it might reduce the user fatigue. It is faster, more efficient interaction, and more importantly, this point is more importantly because The eye tracking technology will provide high rate of sampling so that it means once you look at it, it will immediately generate multiple prompt input points. So if you just only need to click the mouse, you need to click a lot of time. But for the eye gaze, you just have a look, and the eye tracking device will give back a lot of prompt input points, and more prompt input points somehow will increase the accuracy of the segmentation. So this is the pipeline of the our method called GazeSam. We just first the user sit there and we have eye tracker. We do the collaboration. It is only for once, and then we just collect the data. And after that, we have the data. We do a short prompt transformation to let the segment anything model to use, and then after that, we do the real-time segmentation and get the mask. I will show some demo later. And in this slide, I show the user interface we designed that we enable the radiologist to, if you want to read the image, you need to screw the mouse to change the slice, right? This software is enabled that. So the red circle here means the eye gaze here. So it is segmenting the kidney slice. And also in this experiment, we just used the most simple eye tracker. It is sticked on the monitor. So user will just sit in front of it and look at the image. And the results show that our GazeSam achieved like half of the time cost compared to the mouse interaction. We have the comparable segmentation accuracy. And this is the segmentation result that we achieved, like eye gaze-based, mouse-based. They are pretty similar to each other. So this is the demo that I just talked about. So the left one is just on the same slice. You see the red circle is where I am looking right now. And the segmentation will like immediately get you back. And the left part, the right part is that we enable the radiologist to use the mouse to scroll down to change the slice. You see, if the radiologist want to segment the kidney like in multiple slices, they just need to look at the kidney and scroll down the mouse. It's pretty simple and fast. So we also test on a 2D natural image. So you see this demo? Yeah, it's like working like this. Okay, now let's have a conclusion of these two studies so far. We integrate eye tracking into computer-aided diagnosis system. We want to supplement more expert knowledge for lesion detection and diagnosis. And also we properly use the eye to replace the replicate mouse operation for real-time segmentation, like the demo I just showed. For the discussion and the future works, we have so far many promising findings. We believe that human-centered AI is the future, and it is safer, more controllable compared to those pure AI. And we also believe that more works are necessary to understand where and when human input is more necessary, because that's important in the later fusion between the human and the machine. And more works are necessary to combine power of human and computer recognition for a better AI system. So our lab name is Hybrid Intelligence Lab. So because we want to finally one day implement all these things. Yeah, thank you.
Awesome. Thank you so much for the talk. And I guess before we move on to questions from the audience, let's give our speaker a round of virtual applause.
Yes.
And yeah, the floor is now open for questions if anybody has any.
So I have a
I
question.
have a question. Oh, go ahead.
So, sorry. So the camera, are you using Connect for tracking? What kind of camera is you using? That was my question actually. So tracking those informations, eye tracking.
Okay. For the eye tracker, there's two types. One type is let me see. One type is just like this, a bar, very small. It is stick on the monitor. I believe this device is called Toby, and it is used to track the eyes. Pretty lightweight and flexible to use. And another one is called, it's like this. It's a desktop based. It's just put on the table in front of you. So they have both camera and also the radar.
So what kind of information it tracks? It's like some location informations with, or what
Oh, so
else?
yes, they track the like coordinate.
Mm-hmm.
Because before the experiment, we will do the collaboration. Collaboration means they have multiple dots to let you see. So during your eye move, the
Mm-hmm.
eye tracker will record where your eye is focusing on. So, and then it just recorded the coordinate of it. So during the experiment, they just will calculate based on the calibration coordinate, and they will get a bunch of eye gaze coordinate.
Okay,
That
sure.
is the
Thank you.
raw data.
Thank you.
Yeah, so I have another question about the gaze where, so you embedded the, I guess, how long the gaze was in the grid. Is there any information about like the order of the gaze, I guess? Like, because I would assume a radiologist would look at, I guess, the most common quote unquote areas first. And maybe that might not be the longest gaze, but that might be the first place they look at.
Yes, yes. I am totally agree with you. So that is one part of the eye tracking tech application that can be utilized, because different radiologists will have different style of reading images. So they will have preference when they see read image. They will, for example, some radiologists would choose to first look at the left and the right, and some would choose like look at both side during the slice change. So those are not controllable, I think. So in current study, we only study the location things. For the order things, we might need to utilize later, but we need to carefully thinking about how to utilize this kind of information, because different radiologists have different kind of style.
Okay, thank you.
Ben, I have a more of a kind of how do you see the application of this your eye tracking work? Because I understand at the time of inference, you still need that eye gaze, right? So it's kind of human in the loop model. Like even at the time of inference, you need somebody to be looking. So just out of curiosity, like what do you think is the application? I mean, it's the level of expertise that you can lower. The human in the loop, they just need to be looking roughly in the right direction for your model to be able to make a prediction, versus like the human needs to be a top level expert to figure out the disease. Like what's the target application here?
Okay. I'm not sure I'm fully understand your question. So
Yeah. Okay, let me try to explain this further. Like it's human in the loop
yes,
model, right? So the human needs to be there.
yes,
So
yes.
so the question is like if the radiologists still need to look at the image, right, to get that final prediction,
Yes.
then it's not saving their time and effort, or is it?
Because
So
we
like,
want to.
what's the utility here?
So you see, we want to bring you guys a concept like radiologist-centered AI. So the whole system, computer-aided system, is built around the human. So the basic pipeline does not change. So the saving time part, I believe, is lying on the suggestion of the AI, the help of AI. So after because we still need the human, right? We want them to see the image. And after the reading, we can get their expert suggestion. So we input those kind of expert knowledge into the model. It will help like what kind of region is more important for the model to analyze, and what kind of region is the radiologist does not look at. So those regions might be more important, right? Are missed by the radiologist. And so this is kind of a future.
Okay. So in future, you assume that, okay, the model has already learned this information, which areas are more important.
I would not say like the model have already learned, but because the gaze pattern is hard to learn. Because we want the expert in a loop, is because we want the model work, right?
Okay.
And also at the same time, we try a lot to reduce the processing time, because we do not want to bring much trouble to the radiologist.
Okay. Okay. Thank you very much. Just like one last comment. Have you done any experiment where like people are deliberately looking at the wrong area? Like what if this information, this part of the input is deliberately corrupted? Like what happens? Like, I mean, if you give it to an expert radiologist, I'm sure they're looking at the right area all the time, but I can sit in front of that, system and start looking at the image just randomly, like from top to bottom. What happens then?
For the experiment, we did not try like that, like you said, but it is pretty interesting if we can try one day and find out how it works inside. It's a pretty good suggestion.
Yeah, or maybe like it's human in the loop or machine in the loop, or maybe machine can tell me which area should I be looking at instead of I telling the machine which
I think
area we should be
that is the most important part in 3D, right? So that was my question before, that particularly the example that you are showing in the screen, that is a lung city.
Yes.
And you are particularly looking at like the 2D plane of the lung city and look at the eye glaze on the 2D plane, but there is also a Z dimension, right? So why not to look also at the Z dimension to identify the particular slides that are important for making a diagnosis, and look at the eye gaze and all the dimension? Because usually when the radiologists open the study on their screen, they usually look at 3 views. They look at the coronal, sagittal, and the axial, all the things at once. So I think your eye gaze should be looking at all the 3 views, not only a single view from the 3D.
Right. You're right. So for the experiment so far, we only focus on the axial view, because it is the most important view for the radiologist. But you're right, other 2 view is also useful.
Not useful, because you will not identify the axial view until you find the particular like image which has the information, right? And that takes the most of the time for the radiologist to scroll through the volume here and there, So
Yeah, actually in the software, in one of our software, we enable 3 view. So that is ongoing. So for the current study, so far published study, we only study on 1 view. Am I answer your question?
Okay, yeah.
Any other questions from the audience?
Thanks for the nice presentation. I have a quick question about, or more a comment. Last year at RSNA, there was a lab at Johns Hopkins. They, like annotating data is the most expensive task, right? So what they showed at RSNA was they annotated 8 million CT slices, and they used some active learning methodology. And they said, like, if you did it just regular way, it would take 30 years. And with their active learning, they reduced that 30 years to 3 weeks. So it's like an oral presentation at RSNA last year. And then this year, so that was November 2023. And then this year at GTC, which is March 2024, and the NVIDIA team, right, they had this, they released a 3D foundational model called Vista 3D. Okay. And same thing, the same idea that, okay, how can I reduce the number of clicks to get a segmentation? Might be unfortunately the NVIDIA one is not, it's like it's not open source, so it's very hard to you have to get access to NVIDIA model, but the John Hopkins model might be a really interesting case, right? So they've released the data set, and I don't know if you can speed up that 30. Okay, they went from 30 years to 3 weeks. It's still a lot of time. With so if you can show that, yeah, maybe if you had an eye tracker, can you go even faster? And I think they focused on normal organs, and the second part was like, okay, what we really care about is like tumor segmentation. So I've seen people spend up to 500K, like trying to segment tumors. Uh, it's just really expensive now to get good
Yes.
data set of. So both of those, it would be nice to see, or if there's some ways to speed up those segmentations.
Yeah, you're right. Thanks for a suggestion. Maybe, yeah, I can find out this direction if we can do some result there. Thank you.
I had a quick question about the eye tracker itself. So how sensitive would you be to the type of eye tracking? So let's say you have a very noisy eye tracker, which has a large variance in how it tracks. Would your method would your method need really precise eye trackers, or would it what
Yeah,
would
that's
yeah.
that's a good question. So yes, how to utilize the accurate eye gaze information is very important. So you see, the data that we collected from the eye tracker, it might not be so accurate. That's a big issue. So in this study, we're trying to reduce that kind of negative effect to the smallest, like we use the patch here. So if you have a little bit calibration error, like you're looking at here, but the point is actually showing here. But if we can make it in the same patch, we only calculate the importance of the patch. Let that patch represent the importance of the region. That might reduce the negative effect of the noise you said.
Got it. And for the SAM-based approach, would you need to have precise
For the
ones?
SAM-based, actually, let me see. For the SAM-based, actually, it is more interesting because we originally tried two type of prompting segmentation, like 1 point and all point. So if I only enable 1 point, it represents you only use the current eye gaze point, like the red circle here, to segment. But I can also look many points and generate many prompting points and to let it to segment the object. And the second one is shown more realistic.
I see. Got it. Okay, thank you.
No worries.
Any other questions? I guess if not, then let's thank Bin again for the wonderful talk. And if you have more questions or want to get more insights, feel free to reach out to him, or you can reach out to us and we'll put you in touch with him.
Sure.
We'll have the recording up on our YouTube channel later, either today or over the next few days. And we will see you all next week. And thanks again, Ben.
Thank you. Thank you too.
Thank you very much, Manu.